What's wrong? Anyone a link बरोबर तर दिली ना? Hi, my name is Mayur. I'm welcoming you on our practical platform. We are looking at the solution terms, which is the last part of our chapter, which is mole concept. Okay, let's begin. So, solution. What is solution? See, solution is a mixture of two or more substances. It is a mixture of two or more substances, or we can say that solution is a homogeneous mixture. Solution is a homogeneous mixture of two or more substances. Now, what is mean by homogeneous? Homogeneous means something which is uniform throughout. Something which is uniform throughout is called as a homogeneous. Now, what are some of the examples of a homogeneous mixture? We know that sugar is dissolved in a water completely, right? So sugar dissolved in a water, you can say a sugar solution or syrup. Sugar solution or syrup is nothing but what? It's a solution. It's a homogeneous mixture, so it is called as a solution. Or a salt dissolved in water. Salt dissolved in water will give you what? A salt solution that is also uniform throughout. That is also called as a solution. Now everything is not solution. Solution is a mixture, right? But whenever you get a mixture, those mixtures should be uniform or a homogeneous. That means the solute and solvents phase should become one. Then and then only it is called as a solution. For example, if you mix a sand with a water, if you mix sand with a water, it will never be called as a solution. It will only be called as a mixture because it is a mixture. Sand plus water is a mixture, or oil plus water. You can also call that as a mixture. Okay, but you can't call that as a solution at all. Okay, okay. So let's see molarity. Now, what is mean by molarity? See, molarity is is a solution term being used for quite a while now. People use it every now and then. How can we use it? The number of moles, the number of moles of solute dissolved in a 1 liter. Number of moles of solute dissolved in a 1 liter or 1000 ml of the solution is known as molarity of the solution. Or in other words, the molarity of solution would be called as number of moles of solute, number of moles of solute divided by volume of solution in liter. Okay, now there are, this is not the only term that is used as a molarity. It can also be used in some other form. Let me give you that some other. What is that other form? Let's suppose w gram W. Now what is mean by number of moles? Number of moles is equal to amount of substance divided by its molecular mass or its molecular weight, right? So you have number of moles of solute, right? So suppose W grams of solute, W grams of solute dissolved in V ml of solution. Okay, having molecular mass or molecular weight capital M, right? So that means what? That means number of moles of solute, number of moles of solute will be equal to W by M, right? Now VmL of solution, VmL of solution having W by M moles of solute, right? Therefore 1000 ml, no, We have already said in the definition, the number of moles of solute dissolved in 1 liter or 1000 ml of solution. Therefore, 1000 ml of solution will have, now what you will have? Cross multiplication, right? That will give you W by M into 1000 divided by V ml. So basically your molarity is also denoted by a capital M. So molarity is equal to W into 1000. W is what? Amount of solute that you have taken. M is what? Molecular mass. I would rather write here molecular mass of solute into bracket M into volume of solution in liter. Volume of solution in liter. So that is what the formula, final formula of your molarity is all about. Your molarity is equal to amount of substance in grams into 1000 divided by molecular mass of your solute into volume of solution in liter. Now volume of solution would always be given in, sorry, this is not liter, okay? It is in ml. Volume of solution in ml. It will be always be given in ml, and that is why we are multiplying it by 1000 so that it will be getting converted into a liter. Okay, that is how you can find out the molarity. Okay, so let's move ahead with this. Now molality. Now what is molality? First of all, let me tell you why was molality adopted. See, you can look at the molarity here. If you look at the formula of molarity is equal to W, that means weight of solute in grams into 1000 divided by molecular mass of solute into volume of solution in ml. Now we know that with temperature, volume also changes. That means if the temperature changes, the molarity of the substance might change. Instead of might, I would say it does changes. Because if you increase the temperature, the volume will also increase. If the volume increases, since volume is in the denominator, if the volume increases, obviously molarity would decrease. On the other hand, if the temperature decreases, the volume will also decrease. If the volume will decrease, obviously the obviously the molar value of molarity will increase. And that is why with temperature, the value of molarity can change. But molarity is independent of temperature. It is independent of temperature. Why? Because you are having here the mass, the number of moles of solute. You still have a number of moles of solute. You're still having that. Whatever we had in the last term, which is molarity, we still have it in molality. In molality also you are having number of moles of solute, but this time it is dissolved in 1000 grams, or 1000 gram is also equal to 1 kg, right? So it is dissolved in 1000 gram or 1 kg of a solvent. In previous case, if you remember, it is the amount of moles of solute dissolved in a volume of solution in liter. It was a volume of solution. This time it is not solution. It is around 1000 gram or kg of solvent. This is known as molality of the solution. In other words, molality is equal to number of moles of solute divided by mass of solvent in grams into 100. Actually it is not 100, it is 1000 because you are taking it into kg, right? So suppose let's take it again, number of moles of solute. Number of moles of solute will be equal to what? Again it will be, right, W by M, right? It will be W by M. Now you are dissolving that in, let's suppose you are taking grams right now. Let's suppose you are taking that is in Y grams. Y grams of, and obviously that is multiplied by what? 1000, right? Therefore, your molality is equal to W into 1000 divided by molar mass absolute into Y, where Y is what? Y grams, I would say. Y is equal to mass of solvent in grams. Mass of solvent in grams. So that is how the formula of molality is all about. So everything is same. You can see here. See, everything is same. In molarity, you have W, right? In molarity, you have molecular mass. In molarity, you have 1000 multiplying to it. But only factor which was different is this. Here you have a mass of solvent in grams, and there you have volume of solution in milliliters. So that's the difference between molality and molarity. Let me repeat it once again for you. The value of molarity might change with temperature. The value of molarity might change with temperature because in molarity you also have a term called a volume, and volume changes with the temperature. So if the volume changes with temperature, obviously molarity will also change with the temperature. As far as molarity is concerned, in molarity we do not have a volume, we have a mass, and mass of a substance does not changes with temperature, and that is why molality is independent of a temperature. Okay, chalo, let's move ahead with this. Next, mole fraction. What is mole fraction? See, the ratio. What is mole fraction? Mole fraction is the ratio of number of moles, of the solute or solvent present in a solution. It is the ratio of number of moles of solute or solvent present in a solution to the total number of moles present in a solution. Now suppose number of moles. So basically what is it? It is the ratio of number of moles of solute divided by total number of moles. That's it. Or it is the ratio of number of moles of solvent divided by total number of moles. Now total number of moles will be what? Total number of moles will be number of moles of solute plus number of moles of solvent, right? And to the numerator you have number of moles of either solute or solvent, whichever is been asked, whichever. Let's see, let's start with this. See, number of moles of solute. Suppose number of moles of solute is a small n, okay, and number of moles of solvent is capital N. Okay, let's suppose number of moles of solute is a small n, number of moles of solvent is capital N. Then what is mole fraction of a solute? Now mole fraction is also indicated by this term, okay? It is also called as phi. Now phi 1, mole fraction phi 1 of solute would be equal to what? Number of moles of solute divided by total number of moles. Total number of moles will be what? It will be equal to n plus n, right? Small n plus capital N. Similarly, you can also have a mole fraction. Now it is another term. So let's take is phi 2. Mole fraction phi 2 of solvent. That will be equal to what? That will be equal to capital N, number of moles of solvent divided by total number of moles. Now again, total number of moles will be equal to what? It will be equal to n plus n. Okay. So if you're taking addition of phi 1 plus phi 2, you can see that n divided by small n plus capital N plus capital N divided by small n plus capital N. So this total becomes n plus n divided by n plus n, and that is equal to 1. And therefore, the mole fraction of solute plus mole fraction of solvent will always be equal to 1. Mole fraction of solute plus mole fraction of solvent will always be equal to 1. Remember that it will never be different, and that is why, and therefore phi 1 is equal to 1 minus phi 2, or phi 2 is equal to 1 minus phi, like that. That is how you can use the mole fraction. Okay, so basically mole fraction is the number of moles of solute or solvent divided by total number of moles present in the system. That is what is called as mole fraction. And summation of mole fraction of all the components, summation of mole fraction of all the components present in a system will always be equal to 1. You had already seen that derivation. Okay, so moving ahead. Now, solution percentage calculation. The percentage calculation are really helpful. If you have checked the packets of sachets or packets of shampoo, soap, especially the one which has preservatives, for example, tomato sauce, ketchup, okay, then some of the other products, you can look at the Raymond's, Maggie. If you look at the packets of this, you will always find this percentage weight by weight, percentage weight by volume, or percentage volume by volume. This term they use to express what expression. See, let's look at it one by one. The first is percentage weight by weight. What is mean by percentage weight by weight? That means it is the mass of solute present in per 1000 gram of the solution. Mass of solute present in per 1000 gram of the, sorry, not 1000, what I'm saying, 100, per 100 gram of the solution. For example, if you have a glucose, let's say if you have 6 grams of glucose dissolved in 100 ml of water, then what do you call it? You will call this as 6% W by W, weight by weight. That means you have 6 grams of glucose dissolved in a 100 ml, sorry, not 100, 94 ml, 94 ml of water, because this 94 plus 6 is equal to 100. Okay, they are not said the 100 gram of the solution, not solvent. So when you have 100 gram of the solution, it will be considered as the mass of solute plus mass of solvent. So that means 6 grams of glucose dissolved in 94 gram of water, you will have 100 grams of total solvent having 6 grams of glucose. Then you can call it as a 6% weight by weight of glucose solution. Okay, you can say simply term mass of solute in grams divided by mass of solution in grams into 100. Okay, that will give you percentage weight by weight. Next, a percentage weight by volume. Now again, you have a solute as a mass again in a grams, and volume goes in ml. So this is given as a mass of solute. This is given as mass of solute present in per 100 ml of solution. Again, in the previous case, we have per 100 gram of the solution because it was weight by weight. Here you have a percentage weight by volume. So it is given as mass of solute present in per 100 ml of the solution. Or in other words, percentage weight by volume is equal to mass of solute in grams divided by volume of solution in ml multiplied by 100. That will be percentage weight by volume. Okay, so moving ahead, percentage solution. Now percentage solution concentration terms. Third, percentage volume by volume. What is percentage volume by volume? Again, you will again have a volume of a solution in 100 ml as a denominator, but to the numerator you have a volume of solute. Now you have volume of solute present in per 100 ml of the solution. Or in other words, percentage V by V, percentage volume by volume is equal to volume of solute divided by volume of solution in ml. Percentage volume by volume is equal to volume of solute divided by volume of solution in ml into 100. That is called as percentage volume by volume. And last, the parts per million, ppm. The ppm term is actually used when you have concentration of solute very less. When the concentration of solute is very less, or I would say negligible, then you use the term called parts per million, ppm. ppm is equal to, you can see here, mass of solute. It is, we have used it once in one of our numerical in the earlier lectures. Mass of solute divided by mass of solvent, that multiplied by 10 raised to 6. Now you all know 10 raised to 6 is also called as 1 million. Basically 10 lakhs. 10 lakhs is equal to 1 million. That is why the parts per million, the parts of solute present in 10 raised to 6 parts of your solvent. So basically mass of solute divided by mass of solvent in 10 raised to into 10 raised to 6. That is what is called as parts per million. So these are some of the concentration terms which you might need to use while solving some of the numericals. Okay. Chalo. Moving ahead. Ideometry. Now, what is mean by ideometry? See, this is a special technique. This is a special technique that is being used for the amount of gases evolved in a particular reaction. By using this method, you can find out how much amount of gas has been evolved in that particular reaction. And whatever amount of gas you have, that reaction has evolved, from that you can find out the stoichiometry of the other reactant, and that will obviously help you understand that how much amount of solute is giving or releasing how much amount of gas. Okay, so what happens in ideometry? It's a special type of tube. It's a special type of tubes where gaseous reactions are being carried out, and this tube is graduated in a millimeters for volume measurement. That means you have a grading over that tube in the form of millimeters that can give you the amount of gas evolved in a volume. Okay, so what do we do in ideometry is that you take the reacting gases. Okay, you take whatever reacting gases are there. Okay, then you explode them. You make sure they explode in presence of oxygen. You explode them in presence of oxygen. Okay, obviously also giving a spark, because bare oxygen will not make a spark in those gases. Okay, you have that gas, oxygen, and that spark. Okay, by using that, those gases explodes, and whenever the explosion is formed, it's a combustion reaction. Okay, it is not like it's an explosion or something like that. Yeah, it is an explosion, but it's a small explosion, and in that small explosion, this small explosion is nothing but a combustion, and in that combustion, your gaseous reactant will react with each other to release different gases, and those gases are then being absorbed. Those gases, because what happens in a general reaction otherwise, if the reaction happens, gases evolves, then those gases gets escaped. Those gases gets escaped into the atmosphere, and you will never know how much amount of gas was escaped, and then how much reactant you have taken, and then it will be also difficult to find out the mole ratio. What you do here is that you make sure that there's a spark in the reacting system, and then when that happens, it releases the gas. Those released gas then absorbed by some suitable reagents. And by taking those reagents, you can find out how much amount of gas they have absorbed. Okay, so there are different gases being absorbed by different solvent. Okay, because see, if you have CO2, SO2, Cl2, these gases are being absorbed in KOH. Why? Because if you try to dissolve CO2 gas in a solvent called water, it will give you H2CO3. SO2 will give you H2SO3. Cl2 will also give you another acid. So you need to make sure that whatever gases that is being dissolved in solvent, it should not react with it. Because if it reacts, you will never be able to find out how much gas was dissolved, right? So that is why CO2, SO2, Cl2, these are being dissolved in KOH. Okay. Ammonical CuCl2, or I would say ammonical cuprous chloride. It is being dissolved. It is being used for dissolving a gas called CO. CO means what? Carbon monoxide. Then you have a turpentine oil. Turpentine oil is used for dissolving ozone gas. Then you have alkaline pyrogallol. Alkaline pyrogallol is being used to dissolve oxygen gas. Then lastly, you have a water. Water is used as a solvent to dissolve gases called ammonia and HCl. And if the gas itself is a water, then you need to use CuSO4 as a. So CuSO4 can be used to absorb the gas which is water. Okay? That is what ideometry is all about. We will see some other part of ideometry also. Okay, let's look at here. See, you need to remember one more thing. Ideometry is mainly based on Avogadro law. That is what? Whatever volume of gas being evolved, this volume is directly proportional to N. Your amount of volume of gas is directly proportional to number of moles of gas. That is according to Avogadro law. And we know that, right? Whatever amount of volume being evolved by the gas, that will definitely give you number of moles of that gas at the same temperature and pressure, obviously. That is provided if you keep the temperature and pressure constant, because if the temperature varies, the amount of volume of gas will also vary, and that might mislead you to the number of moles of gas. For example, suppose if you are having a 22.4 liters of the volume of given gas at STP, okay, standard temperature pressure. So you know that 22.4 liters of volume, that means you have a 1 mole of that gas, right? So you know you have 1 mole of a gas, and suddenly suppose temperature drops. If the temperature drops, that volume will also drop to whatever amount. Suppose if it drops to 22.4 to 11.2. Okay. Now 11.2 is what? 11.2 is a half mole. Half mole. So that means you have misled it. That is why, to keep the volume constant, you need to make sure temperature and pressure are also constant. Because if the volume is not constant, the number of moles will change. If the number of moles are changing, the whole calculation would be different. Okay, that's it. Remember that thing always. Next, burning of hydrocarbon. So this reaction people have been using this reaction for quite some time to find out a formula for a particular hydrocarbon. So what do is that they take particular hydrocarbon, they burn them. Okay, after burning, obviously the carbon part of hydrocarbon will form a carbon dioxide, CO2. The hydrogen part of your hydrocarbon will always form a water. Then amount of moles of CO2 or water formed, from that you can find out what was the hydrocarbon that you took initially. So look at the formula here, CX plus HY. CX plus HY, this is what is CX and HY? Suppose you have a CH4, then you have what? C1H4. So in that case, your X will be 1 and Y will be equal to, okay. So CXHY in the gaseous form, when it undergoes a combustion reaction with the oxygen, so CXHY plus X plus Y by 4O2, it gives you X moles of CO2. So X moles of CO2, that means whatever number you have on the carbon, same number of CO2 will always be formed. Look at here. Suppose you have a C5H12. The C5H12 will always give you 5 CO2. That means in C5H12 you have X is equal to 5, right? And so that gave you 5 moles of CO2. So that is why CXHY in the gaseous form on combustion reaction with X plus Y by 4 moles of O2 gives you X moles of CO2 and Y by 2 moles of H2. Again Y by 2. So let me give you one more example. See, you have a methane. Okay. Methane on reaction. Let's take what they're saying, X plus Y by 4, right? So you have one carbon, right? So one carbon, that means X is equal to 1. Y is how much? Y is 4, right? So Y is 4 divided by 4 into O2. So 1 plus 4 by 4. 4 by 4 is 1. And 1 is already there. So 1 plus 1 becomes what? 2. So CH4 plus 2O2. It will give you what? It will give you CO2 and 2H2. So you can always see the reaction is balanced here. That is how this formula is justified. So if you look at the reaction here, so this is your Y. Your X is equal to 1 here. Y is equal to 4, right? So that is balanced with the oxygen. Now what they are saying, you are getting X CO2. So X is 1 here. So you're getting 1 CO2, right? Then you are getting Y by 2 H2O. Now Y is 4, right? Now Y by 2, that means 4 divided by 2. So 4 divided by 2 is equal to 2H2O. Okay? That is how this formula is justified. So remember this formula in a way that Cx plus Hy plus, or remember one thing. If you remember this thing, you will never be able to remember, you will never be needed to remember this formula. See, whatever hydrocarbon you have, I'm saying hydrocarbon, remember my words again, whatever hydrocarbon you have, if it is undergoing a complete combustion with oxygen, if it is undergoing a complete combustion with oxygen, remember whatever carbons you have, every carbon will be converted into CO2. Every carbon will be converted into CO2 and every hydrogen present in the hydrocarbon will be forming the water. Then whatever amount of oxygen being needed to form that CO2 and H2O, let's count that and then add it to the initial amount of your hydrocarbon. It is that simple. Okay. But for the time being, let's remember the formula Cx plus Hy in addition with X plus Y by 4 moles of O2 gives you X CO2 plus Y by 2 moles of H2. Similarly, there can be some hydrocarbon which is having an oxygen also. Now, I cannot call that as hydrocarbon because that is not hydrocarbon then. Let's take an example of alcohol. Alcohol, the people who are studying organic chemistry, they don't call alcohol as a hydrocarbon having oxygen. Okay. But to make the things easier or to make the things easier for you to understand, let's call it as a hydrocarbon containing oxygen. Okay, because hydrocarbon already contains hydrogen, oxygen. So if you have that hydrocarbon or alcohol, then you have a CXHYOZ, right? Where X, Y, and Z are indicating the number of atoms of carbon, hydrogen, oxygen respectively. Plus X plus Y by 2 minus Z by 2 moles of O2. So on reaction or combustion with that much amount of oxygen, you get X moles of CO2 plus Y by 2 moles of H2. That is constant. This part is constant in both cases. Okay. Remember this formula. It will come handy to you or handy to us while solving the numerical that we're gonna solve. Okay. So moving ahead. See what volume. Now we will start the numericals. Okay, we have done enough with the theory. Physical chemistry is more about the numericals, and you will understand the concepts in a broader way by solving the numericals. Okay, so what volume of oxygen at STP is required to effect complete combustion. What volume of oxygen at STP is required to effect complete combustion of 400 centimeter cube of acetylene, and what would be the volume of CO2? Okay, let's write the reaction, normal reaction of acetylene first. C2H2, that is what is called as acetylene. This is your acetylene. Plus, we don't know how much amount of oxygen we might be needing. So on reaction with this, it gives you 2 moles of CO2 plus 1 moles of H2, right? So you can see you might require 5 atoms of oxygen here. 5 atoms of oxygen, that means this might become a little complicated. So let's multiply it by 2. That means let's take 2 moles of C2H2 plus, now you're sure that you get a 10 oxygen atom, that means 5 O2, right? So 2 C2H2 plus 5 O2O2, 5 O2, it gives you 4 CO2. Plus you got how many hydrogen? 4 hydrogen, 2 H2. So 2 oxygen here, 2 oxygen. So total overall it's balanced. So you can see here the 2 volume of acetylene C2H2. What they are asked is what volume of oxygen at STP required to effect complete combustion of 400 centimeter cube of acetylene, and what would be the volume of CO2 formed. So 2 volume of C2H2 requires 5 volumes, or I would say 5 moles, 5 moles of oxygen at STP. So therefore 400 volumes of C2H2 would require is equal to 400 into 5 divided by 2, right? So 2 into 2, 2 2s are 4. So 200 into 5 is equal to 1000. So 1000 centimeter cube of oxygen would be required. Or let me tell you, instead of going every time by this cross multiplication and all that, see, sometime in exam you might needed to solve the questions directly, or I would say I use that term that solving the numericals in air. That means in air means what you are imagining, right? You are imagining if 2 moles of acetylene required 5 moles of oxygen, right? So what is the ratio? Ratio is a 2 into 2.5, right? So amount of oxygen required is always 2.5 times of the volume of acetylene, right? So if you have 400 volume of acetylene, so 400 into 2.5 becomes how much? So you can always solve it in a that way also. To make you understand in a better way, I'm writing here everything, okay? But wow, you should be practiced of doing it in the air, okay? So that is with the amount of oxygen required. Now what else they ask is, what would be the volume of CO2 formed? The CO2 form is already given there. See, 2 volume of acetylene is giving you 5, sorry, not 5, 4. 2 volume of acetylene is giving you 4 volume of CO2. Then 400 centimeter cube or 400 volume of acetylene will give you what? Twice of it, no? It would give you 800 centimeter cube of CO2. And isn't it straightforward? No need to write it and no need to go for that cross multiplication thing and all that. See, this sometimes sometimes it becomes more complicated by going in that way. You can simply calculate it, okay? More often than not, it's a whole number. Sometimes it's a fraction number also, but the fraction number is also not that complicated, okay? Chalo, moving ahead with this. So basically you get 800 centimeter cube of CO2 here, because the ratio of amount of acetylene took and amount of CO2 formed is 1:2. So if 2 moles of acetylene is giving you 4 moles of CO2, Obviously, 400 centimeter cube of acidity will give you 800 centimeter cube of, okay, and so on. So, moving ahead, next. Gaseous hydrocarbon. A gaseous hydrocarbon requires 6 times its own volume. Gaseous hydrocarbon requires 6 times its own volume of O2 for complete oxidation and produces 4 times its volume of CO. What is the formula? Now, I don't remember which exam this question was asked in, but it was definitely it is definitely from some exam. Okay, I did not mention that here. But let's go that by that formula. What was the formula? CXHY reacts with X plus, what was it? Y by 4, right? X plus Y by 4 moles of O2. It gives you what? 4 times its volume of CO2. Okay, that means CO2 that you got is 4. So basically X is 4 now. X is 4. Or let's go by this. X plus Y by 4 is equal to what? Is equal to 6. What is what they have, that is what they have said, no? A gaseous hydrocarbon require 6 times its own volume of O2. So this volume is what? X is X plus Y by 4, right? So X plus Y by 4 is equal to 6. Now to balance this, we need to multiply everything by 4. So that would give you what? That would give you 4x plus y is equal to 20. Now we already know that x is equal to 4, right? Because they have already told us that it produces 4 times its volume of CO. That means whatever volume you have here, 4 times that CO2 is produced. That means you get a 4 CO2 now. Remember, the number which is before this carbon in CO2, that number will be having of carbon. That means X is 4. So putting the value of 4 here, you get 4 into 4 plus y is equal to 24. Now that will give you what? That will give you 16 plus y is equal to 24. And therefore y is equal to 24 minus 16 is equal to 8. So that means y is 8 and x is 4. So that will be our formula is what? C4H8. That is our hydrocarbon. And that is your formula. Now let's confirm it if it really requires 6 moles of oxygen or not. C4H8. We don't know how much moles of oxygen, so I'll keep the place there. Now you get the 4 CO2 plus 4H2. So 4 into 2, 8. 8 plus 4, 12. So yes, you require 6 times the volume of hydrocarbon as oxygen. You can see that clearly here. That means our answer is right. That is C4H8. So it might be C4H8 is obviously what? It's alkene. It's a butane. Okay, C4H8 is nothing but a butane. So that is how you can use that formula for solving this numericals. Okay. Moving ahead. If you have any doubt, you can ask me in the comment section. If no, then we can move ahead. Moving ahead. 1 mole of chlorine. A 1 mole of chlorine combines with certain weight of metal. 1 mole of chlorine combines with certain weight of metal, giving 111 grams of chloride. Same amount of metal, the same amount of metal can displace 2 grams of hydrogen from an acid. The atomic weight of the metal is. Now let's see. Suppose if we don't know what is the atomic mass of your metal, we are not sure of that, but we know for sure that the metal which can displace 2 moles or 2 grams of hydrogen. That means 2 moles of hydrogen. Okay, we had seen that already. So the metal which can displace 2 moles of hydrogen, 2 moles of hydrogen from a given acid should be, it should be the metal whose valence is 2, or the metal which must be belonging to alkaline earth metals. Okay, because for alkaline metal it is something different. 2 grams means it is, sorry, not 2 mole, 2 grams means it's 1 mole, because atomic mass of hydrogen is 1, but molecular mass of hydrogen gas is 2 grams. So suppose if you have a calcium on reaction with H2SO4, it can replace the complete 1 mole of sulfate. You can see here, you get a CaSO4, calcium sulfate, releasing 1 moles of a. Same happens with beryllium, magnesium, calcium, strontium, barium. Basically, the metals which is having valency 2 can do this. The metal whose valency is 1 cannot do this. For example, sodium, potassium, they cannot do this. That means, suppose if it is an alkaline earth metal, since its valency is 2 and valency of chlorine is 1, that means 1 atom, or I would say 1 mole of alkaline earth metal would require 2 moles of a chlorine atom. That means you will require, that means your 11 grams of metallic chloride is having 2 chlorine. Now each chlorine atom's atomic mass is 35.5. So if you have 2 chlorine, 35.5 into 2, it becomes how much? 71. So we need to find out the amount of metal in it, right? So that is why I'm doing this. Let's take the 111 grams of metallic chloride which they have already given. Subtracting from that 71 grams of chlorine, right? 2 chlorine. So we are remain with what? We are remain with the 40 grams of metal. And 40 grams of metal is somewhere close to calcium's atomic mass. And we know that calcium can displace 1 mole of a hydrogen to give you calcium sulfate. And that is why the atomic mass of the given metal is 40 and it is calcium. It cannot be 20. Okay, because 20 atomic mass is of neons and neon does not react with your chlorine. Okay, 80, I'm not sure, but mostly it is of bromine. And bromine is not a metal, bromine is a non-metal. That is why the answer is 40, that is of calcium. Okay, so moving ahead. Next, amount of CaO required when it reacts with 852 grams of phosphorus pentaoxide. Now this is a phosphorus pentaoxide, but you might say, sir, we got 10 oxygen, how could it be pentaoxide? Yes, you have a 10 oxygen, but it is actually a dimer of P2O5. P2O5 plus P2O5 together they give P4O10. So it's a dimer of phosphorus pentaoxide. Okay. Anyway, so what they're saying, amount of CaO required to react with 852 grams of P4O10 is. Okay. Now to understand this, firstly we need to write down it's a balanced reaction. Now remember, the valency of calcium is +2. Okay. And P4O10 always give rise PO4 3 minus. The valency of PO4 3 is 3. It's a phosphate. So basically, calcium oxide reacts with P4O10 to give you calcium phosphate. Okay, and you need to have a 3 calcium for 2 phosphate. Look at this, because 3 calcium's valency will be +6 and 2 phosphates valency will be -6. That is how it will be balanced, calcium phosphate. So 3, sorry, not like this, Ca3PO4. Okay, so for 2 phosphorus you require 3 calcium. That means of 4 phosphorus you will require 6 calcium, right? But 6 calcium will always bring in 6 oxygen. So reaction would be like this: PaO plus P4O10, and it gives us 2Ca3PO4. You can write, you can see if the reaction is balanced or not. On the left hand side, you got 6 calcium. On the right hand side, you got a 6 calcium. On the left hand side, you got the 16 oxygen atoms. On the right hand side also, you got 4 into 2, 8, 8 into 2, 16 oxygen. On the left hand side, you got 4 phosphorus. The right hand side, you got the 4. That means reaction is balanced. So this is the balanced reaction. Now let's find out what they're saying is that if we are taking 852 grams of phosphorus pentoxide, how much grams of calcium oxide is required? So let's find out what is the molecular mass of P4O10. Now the atomic mass of phosphorus is 31. So 31 into 4. Oxygen atomic mass we already know. It is 16. 16 into 10, 160. So 31 into 4, it becomes how much? It becomes 124. 124 plus 160 is equal to 284. 284 grams. And calcium oxide, atomic mass of calcium is how much? 40. We just now saw, right, in the last numerical. 40 plus oxygen is 16. It becomes 56. Right? But we had for a 1 moles of phosphorus pentoxide, you require 6 moles of CO. 1 mole is equal to 56, right? So 6 moles will be equal to 56 into 6. 6 6 are 36. 6 3 6 5 are 30. 30 plus 3, 336. Yeah. So total 336 grams of calcium required for 284 grams of phosphorus pentoxide. How much moles of phosphorus pentoxide they have now? 852. So if for 284 grams of phosphorus pentoxide require 336 grams of calcium oxide, then 852 grams of phosphorus pentoxide will require how much of calcium oxide? We don't know. So let's write x grams. Again, cross multiplication. 336 into 852 divided by 284 is equal to x. Now 284 and 852 divided by 284. We don't know how much it is, but it seems like 28 threes are 580. Sorry, 28 threes are 840. So it must be going somewhere close to it. We don't know. Let's try it if it is multiplied by 3 or not. So 3 4s are 12, 2 1, 3 8s are 24 plus 1 5, 3 2s are 6 plus 2 8. Oh, it is exactly. So 284 ones are 284, 284 3s are 352. So 336 into 3 is equal to how much? 336 into 300 into 3 is 900. 36 into 3, 108. So 900 plus 10, it becomes 1008. Yes. So you will require 1008 grams of calcium oxide. And the answer is yes, here. It's here, B. So that is how you can solve this mole to mole concept numerical also. Okay. Now you might say, sir, we might not remember this atomic mass and all that. So you don't need to worry about it. The atomic mass of most of the elements are being given in the exam. Okay. For some you need to remember, like for carbon, hydrogen, oxygen, that much you can remember, right? But for the heavier elements, it is always been given in the exam. Okay. In fact, in the exam these days, they also provide the atomic or molecular mass of smaller elements, for example, hydrogen, oxygen, for which you might not need even. Okay. But to make the things sure, they have been always given. Okay. So moving ahead. Next, the isotopic abundances. Now you already know, we have already seen that the isotopes, for example, carbon has C12, C13, C14, out of which the 98% or more percentage is a C12 and only 2% is around C14. Okay, so the isotopic abundances of C12 and C14 is 98% and 2% respectively. Then what would be the number of C14 isotope? What would be the number of C14 isotopes in a 12 grams of carbon? Now, suppose if there is no mentioning of this isotope thing, and if I tell you that you have 12 grams of carbon sample, how much, what would be the number of carbon atom in that? What would you do? You know the atomic mass of carbon is 12. I have given you 12 grams only. You will divide 12 by 12, you will get 1. So 1 mole of carbon would obviously have a Avogadro number of carbon atoms, which is equal to 6.02 into 10 raised to 23, right? But here I have asked you what would be the number of C14 isotopes in that 12 grams of carbon sample. Okay, now, so you had already seen here the C14 is how much? 2%. That means 100 grams of carbon sample, 100 grams of carbon sample will be having 2%. No, 2%, 100 का 2 ग्राम मतलब 100 का 2% मतलब कितना? 2 grams. So 100 grams of carbon sample will have 2 grams of C14. Therefore, 12 grams of C12 sample will have how much? Again, X grams of C14. Again, cross multiplication, 12 into 2, 24. X is equal to 24 divided by 100 is equal to 0.24 grams. Is equal to 0.24 grams, right? 0.24 grams of CO2. Sorry, 0.24 grams of C14. So they are asking what would be the number of it, right? Number of it. Then how can we do this? 100 grams will have 2 grams. 12 grams will have 0.24 grams. Now 0.24 grams so this is your amount of C14 now. So amount of C14 0.24 grams divided by what? What you gonna do by C14 now? If C14's atomic mass will be how much? It will be 14 no? For C12 it's a 12, right? Then for C14 it's a 14, right? So 24 divided by 14 into 10 raised to minus 2. So 14 ones are 14, you got 100. Then 14 sevens are 98 to 14 ones are right. So you have a 1.71 into 10 raised to minus 2 moles of C14. So you need to find out the number of C14 atoms. Then what you gonna do? 1.71 into 10 raised to minus 2 into 6.02 into 10 raised to 23, right? 10 raised to minus 2, 10 raised to plus 23 become 10 raised to 21, and 6.02, let's take 1.71 into 6 1. 6 1 the 6, 6 7 the 42, 2, 4, 6 1 the 6 plus 4, so 10.26. 10.26 into 10 raised to 21. So that makes it 1.026 into 10 raised to 22. And which is the closest answer to this? Is this. 1.032 into 10 raised to 22. We have 1.026 because we have ignored 6.02 to make calculation easier. But anyways, it leads us to our answer. Okay, that is how you can find or you can solve this numerical. Next, 35 chlorine and 37 chlorine are two isotopes of chlorine. If average atomic mass of chlorine is 35.5, then the ratio of these two isotopes. Generally, what do they do is that they have given us the ratio and they have asked us to find out the average atomic mass. This time it's a retro way. This time they have given us a average atomic mass and they have asked us to find out the ratio between these two isotopes. Now, what is our general formula for this? Your average atomic mass is equal to, you take the atomic mass of one chlorine, which is 35, right? Suppose its percentage, we don't know how much percentage of 35 chlorine are there, right? Suppose it is X percentage. Okay. So if the 35 wala is X, the 37 wala would be how much? If this is X, it will be 100 minus X. Whatever the X comes, it will be 100 minus X. So 37 into 100 minus X divided by what? Divided by X plus 100 minus X. X gets cancelled, divided by you will have 100. Total percentage is 100. That is what the formula is. So average atomic mass is given 35.5, right? Is equal to 35x plus 37 goes here, 3700 minus 37x divided by 100 goes that side. What do you get? 3550, right, is equal to 35x minus 37x divided by 35x minus 37x plus 12, 3700. So let's send 3700 that side. You get what? 3550 minus 3700 is equal to 35 minus 37x is equal to minus 2x. And 3700 minus 3550 becomes minus 150. So minus 150 is equal to minus 2x. Minus minus gets cancelled. So 2x is equal to 150 and therefore x is equal to 75. So if the x is 75, that means 35 wala chlorine is 75%. Now 37 wala chlorine is how much? 37 wala chlorine is equal to 100 minus x. No, you can see that. So 100 minus x, what is x? 75. So 100 minus 75 is equal to 25. So 37 wala chlorine is 25% and 37 wala chlorine is 75%. So you know what would be the ratio. 75 divided by 25. It has to be 3:1. Now remember what they have asked. They have asked the ratio of they asked the ratio of 35 chlorine to 37. So 35 is thrice the amount of 37. That is why it would be 3:1, not 1:3. Okay. Had it been reverse, it would have been 1:3, but it is not reverse. So remember to focus on these points also in the exam, because they have given you one more option which is exactly reverse of 3:1. That is why answer is 3:1 here. Okay, chalo, moving ahead. Zinc metal. Zinc metal reacts with HCl by following equation. Zinc plus 2HCl gives you ZnCl2 plus H2. Now what they said is that if 0.30 mole of zinc, 0.30 mole of zinc is added to HCl containing 0.52 mole of HCl, how many moles of H2O are produced? Now look here. You need to find out here which is the limiting reagent and which is the excess reagent, because limiting reagent will gonna take you to the amount of moles of product. Okay, so let's reaction is already written. So if you have 1 mole of zinc, you will require 2 moles of HCl. It is clearly written there, right? 1 moles of zinc requires 2 moles of HCl, which gives you 1 mole of zinc chloride and 1 mole of hydrogen gas. Okay, so 0.30 mole of zinc, 0.30 mole of zinc would require how much? would require you 0.60 mole of HCl. Would require 0.60 mole of HCl, right? So you have 0.30 mole of zinc, but out of 0.60 you have only 0.52 moles of HCl, right? That means HCl is less than what required. So the amount of HCl required is 0.60, but we have how much? 0.52. That means your HCl is a limiting reagent. And if it is a limiting reagent, it will decide the amount of hydrogen gas that is formed. So you can see here 2 moles of HCl gives you 1 mole of hydrogen gas. Therefore, 0.52 moles of HCl would give you how much? It's clearly half, right? Where you have a 2 moles of HCl, you got 1 mole of H2 gas. So if you have a 0.52 moles of HCl, you will have a 0.26 mole of hydrogen gas. And that is it. That is what they have asked us. That how many moles of hydrogen gas are produced. And 0.26 moles of hydrogen gas will be produced. Okay, clear? How can we use this limiting reagent and excess reagent to solve such a number? Okay, so moving ahead with this. Next, 2.76 grams 2.76 grams of silver carbonate on being strongly heated yields a residue weighing. We don't know how much it is. We need to solve this reaction first. Silver carbonate. Now carbonate has charge CO3 2 minus. Silver has charge Ag plus 1. That means each carbonate will require 2 silver. So Ag2CO3. But this doesn't balance it because you know that from Ag2CO3, silver will go out as a residue. But what about CO3? CO3 sounds something odd, no? So that is why we might need to take 2 moles of Ag2CO3, which gives me 4 moles of Ag, 2 moles of CO2 gas, and 1 mole of oxygen. Now it is balanced. You got 6 oxygen on the left, 6 oxygen on the right, 4 silver atom on the left, 4 silver atom on the right, 2 carbon left, 2 carbon right. So everything is balanced. So this is the balanced reaction. Every time whenever you needed to solve this mole question, that means mole, mass to mass, mass to volume, or mass to mole, mole to volume, whatever it is. We had seen 4 types of it, right, in gravimetry. You always needed to write the balanced chemical reaction first. Okay? So this is the balanced chemical reaction. Now, so let's see how much silver carbonate we need to take to produce this much amount of silver. So atomic mass of silver is how much? It's 108. You got 4 silver here, 108 into 4 plus CO3. In CO3, oxygen is 3, 16 3s are 48 plus carbon 12. That means you got 60. 60 into 2. So basically you got 108 into 4, it becomes 432. 432 plus 16 into 2, it becomes 120. So it becomes 552. 552. That is for 2 moles, no? Wait. 2 carbon. No. So I went it wrong way. You got CO3 16 into 2. Oxygen becomes 6, no? Just a sec. 3 into 2, 6 oxygen, 96 plus. Yes, it is right. So 552 grams of silver carbonate gives us residue. What we need to focus here is residue, because they have been asking about amount of residue formed from that given amount. Okay, so residue is what? Residue is what? Solid, right? Because this is gas, that is not residue. This is also not gas. But Ag is a gas. Ag is a salt, right? Sorry, what I'm saying. Ag is a solid. So you got 432 grams of silver here. 432 grams. So 552 grams of silver gives you 432 grams of silver. If you divide 552, you will get what? 552 or 250 plus, yes, 276. That means 276 grams of carbonate, silver carbonate will give me or us 216 grams of silver, है ना? इसका मैंने हाफ किया बराबर. If the 552 grams of silver carbonate gives me 432 grams of silver, then half amount of silver carbonate will give me half amount of residue. है ना? This is our residue. As I have told you earlier in the last lecture, residue is the amount of solid that is formed. So if the 276 grams of silver carbonate gives me 216 grams of residue, then 2.76 grams, that means taking two decimal behind, from 276 to 2.76 grams of silver carbonate would give me 2.16 grams of residue. If you take the two decimal behind here, here also you need to take two decimal behind. So it was 216.00. So I took it to behind to give Q, which gave me 2.16 grams of residue. And that is why the answer is 2.16 grams. Okay, so you can solve it simply by doing this instead of going for that, that cross multiplication, all that thing. This decimal point will always help you solve the numericals in an easier way. Okay, so moving ahead. Next, 1 gram of magnesium. 1 gram of magnesium is burnt with 0.56 gram of oxygen in a closed vessel. Which reactant is left in excess? Again, we need to write the reaction. So magnesium valency is 2. Oxygen's valency is also 2. But we are taking O2, no? That means we need to take 2 magnesium. So 2 magnesium plus oxygen gives you 2 Mg. The atomic mass for magnesium is how much? Beryllium, magnesium. Magnesium's atomic mass is 12. Sorry, atomic number is 12, so atomic mass is 24. So 2 into 24. Oxygen is how much? 32. Right? So 24 into 2, 48. So 48 grams of magnesium reacts with 32 grams of oxygen. Basically, for this reaction to happen, 48 grams of magnesium requires 32 grams of oxygen. So question is, if the 48 grams of magnesium requires 32 grams of oxygen, then 1 gram of magnesium would require X grams of water. We need to find out how much. So, yeah, 32 into 1 divided by 48 is equal to X. Now 16 2s are 32, 16 3s are 48. So X is equal to 2 divided by 3. So 2 divided by 3 is how much? 3 6 are 18. You got 2 0. 3 6 are 18. Yeah, something like that. So X is equal to 0.66 grams. So basically 1 gram of magnesium required 0.66 grams of oxygen. But how much grams of oxygen do we have? 0.56 grams of oxygen. So that means oxygen is the limiting reagent and magnesium is excess. Now we again need to go in a reverse way. Reverse way means what? Firstly, we came to know that 48 grams of magnesium is needed, 32 grams of oxygen to react. So therefore we needed to find out, if we have 1 gram of magnesium, how much oxygen is required. So 1 gram of magnesium required 66 grams of oxygen. Okay, but well, we need to go in a reverse way now. So not exactly reverse way. Wait. So see, is burned with so oxygen required is 0.66, but we have how much? 56. So if the 0.66 grams of oxygen requires 1 gram of magnesium, then 0.56, no, we have 0.56 gram of oxygen, right? Then 0.56 grams of oxygen required how much grams of magnesium? And then it will be surely less than 1 gram. We know that. If the 0.66 grams requires 1 gram of magnesium, obviously 0.56 grams of oxygen will require less magnesium, right? So that is why let's multiply 1 into 0.56 divided by 0.66 is equal to grams of oxygen, that is X. So your X is equal to 56 divided by 66. So 56 divided by 66, 0. 660, no, we don't know. 660, maybe 8. 528. 528. How much remains? 32, 0. 66. 4s are maybe. Is yeah, 0.4, yeah, 0.84. So X is equal to 0.84. So basically 0.56 grams of oxygen is needed, 0.84 grams of magnesium to react. But how much magnesium we have? 1 gram, and therefore magnesium in excess is equal to 1 minus 0.84. That will be equal to 0.16 grams. So you have 0.16 grams of magnesium in excess. That is how you can solve this limiting and excess reagent wale numericals. Okay. Now the last one. This is the last one. Now 20 grams of MgCO3 sample decomposes on heating to give CO2 and 8 grams of MgO. What will be the percentage purity of MgCO? Again, we needed to write the balanced equation. MgCO3 on decomposition gives you MgO plus CO. Now, molecular mass of MgCO3, a carbon is 12, oxygen is 48, oxygen is 12, 60, and magnesium is 24. Yeah, so 84 grams of MgCO3 gives us 24 plus 16, 40 grams of MgO and 44 grams of CO, right? So that is the balanced equation. Now you are getting 8 grams of MgO from the 20 gram of MgCO3. So if you are getting 8 grams of MgO, so 8 gram is definitely 5 times lesser than 40, right? That means the MgCO3 that we have taken, that must also be 5 times lesser than 84, right? 5 times lesser than 84 would be how much? 5 ones are 5, 6, yeah, 16.8. So 16.8 grams of MgCO3 would give me 8 grams of MgO. You are already getting 8 grams of MgO. That means 16.8 grams of MgCO3 is pure. Remaining is what? Impure. So 20 minus 16.8 is equal to how much? 3.2. So you have 3.2 grams of MgCO3 as impure. So we need to find out the percentage purity, right? They ask us to find a percentage purity. So percentage purity is how much then? 20 gram contains 16.8% purity. Then the 100 gram will contain 16.8 into 5, right? 16.8 into 5, 16 for 5 is 80, 8 5 is 4, so 84%. Right? If 20 grams of MgCO3 contains 16.8% as pure part, then 100 grams of MgCO3 will contain 84 grams as pure part. So therefore, if the 100 grams of MgCO3 contains 84 as a pure part, that means 84 is a percentage purity. And that is why our answer is 80. Okay, that is it for today. And that is how our chapter called mole concept has been finished. It has been concluded. Okay. Thank you for all of your patience. Now in the next lecture, we're gonna see the chapter called redox reaction. Okay. This mole concept is gonna come handy for us in a chapter called redox reaction. We will explore that from the next lecture. Okay. Thank you all. That's it for today.